Why is it a picture? Oh my god. Why can't you see me? Seth?
Oh Christ, I look like trash.
Why is it a picture of me? I'm so confused.
Because you chose to join without video.
Oh, I don't know how to know.
There's a way to do it.
It
Why
just,
am I
Down to
thinking?
the bottom left corner. Did you say start video? I think.
Video. Okay. Oh, I look so bad though. That's okay.
Oh yeah,
It's
there's a
okay.
little button at the bottom that says stop video that you can use.
Hey,
Oh my
do we have to
gosh,
use
we're
video?
supposed to
Feel
have
self-conscious, I'll
our
just go
picture
do
on
that.
there. I joined without it, but
It's okay, even if I don't see you, I don't care.
Do we have to use video?
Oh, not really.
I'm not interested in using video. I'm just here to listen.
Yeah, exactly, yeah.
Now it's just a picture of me.
Yeah.
That looks
Okay.
like a professional photo. Wow.
Participants in waiting room center. Okay, there we go. That should like. All right. Well, there's still 2 minutes, so let's wait for everyone. You all can see my screen, right?
Yeah.
yep.
Yeah, we
Okay,
can see.
good. Okay, good.
I thought it was my screen for a second. I couldn't figure out why it wasn't working.
This is real.
No, it's a screen share.
Okay. Let me see. I think you can also annotate here, by the way. Remote control. I'm gonna play around with this one more, but I think you can actually annotate this for like everyone to see, but until I figure that out. Okay. I don't want to annotate anymore. Okay. There you go. Okay, so I guess we can start now. So basically, the topic that we should have been discussing today was the Chatelaise Principle. It's mostly qualitative. If you add a chemical stress to something in equilibrium, you basically, or the system tries to restore itself back into equilibrium by getting rid of that stress. It's basically the only thing that you'll need to know. One thing too that I think I want you to remember will be that if you're going to add a solid or a liquid, it doesn't matter at all because the concentrations of solids and liquids are constant. Okay, and
for a private story.
And if you're actually looking at pressure, you're only going to deal with gases.
Hello?
Okay, I can hear you. Okay,
What?
so I can hear you. Okay, so I went through all of these problems in that video that I pre-recorded yesterday. So I guess just go over them as well. One important thing with the Chatelaise principle for temperature, again, exothermic heat is a product and the thermic heat is a reactant. So all of those crap. Okay, but I'd like to go over this problem. Okay, announcement to, I haven't heard from Macmillan yet about iClickers, so I guess no iClickers until further notice. If we don't have one this week, I might just like give you an online quiz, like a really quick one. Okay. Let's work on this problem. So you will be given something like this in a test. So the question is, how will the following changes affect the equilibrium amount of NH3 present. So basically, what here will be the concentration of, or what will happen with the concentration of ammonia, okay, when the following happens. Not write properly, sorry. Okay. Okay, so you're asked here again, oops, got too far. Okay. Okay, what will be the concentration of ammonia basically if all of these happens, or if these happen? Okay, let's go with the first one. How do we go with this? Okay, let's go with the first one. So the first one is oxygen is added to the system. Okay, so since oxygen is added to the system, oxygen is in the reactant side. Okay, if oxygen is in the reactant side, then that means the equilibrium should shift to get rid of that excess oxygen. So this one, oh gosh, this is very sensitive, sorry. So this one should go towards decreasing the amount of ammonia. Okay, let's answer the second one and the rest as a class together. Oops. What happens if you remove nitrogen from this system? What do you think? So you're decreasing, hello? Anyone can answer now.
Just towards the reactants.
To the reactants. Oh, well, you're removing N2 from the system, okay? So you're decreasing the amount of N2. So how do you recover back N2? So not really reactants, but you have to
Product.
yeah, you have to go back to products. So, but we're looking at ammonia here. So it will shift to the right, sure, but you have to, but at the expense of the concentration of ammonia going down. Everyone follow that at this point?
Yes.
Okay, and then next we will have the concentration of water going up. So water here is actually a gas, so we have to take that into consideration. If water here was a liquid, it wouldn't have mattered. Okay, more water. So if you're increasing the concentration of water, how do you get rid of that extra water?
Shift to the left.
It should move to the left, right? Okay. And if you shift the reaction to the left, what happens with the concentration of ammonia?
Increase in ammonia.
Yeah, you have an increase in ammonia. Sounds good. All right, argon is added to the system. So how about this one? So argon is a noble gas. Okay, so just remember that argon is a noble gas. Ooh, cannot spell noble gas. Okay, now adding a noble gas sure will increase the pressure of the system, but it does not increase the partial pressure of all of the reacting gases. So let's just note that down. So does not increase or decrease, actually, does not increase or decrease the partial pressure of gases reaction, whether they're products or reactants. Okay, so this one should actually lead to no change in equilibrium. Okay, so no effect whatsoever in equilibrium. The concentration of ammonia at equilibrium still stays the same. Okay. Number 5, or not number 5, but letter E. The volume of the reaction vessel is increased. Okay, let's just clear some things out of the way. And I'm going to record this, by the way, so this will be up sometime too. Okay. All right, number 5, or letter E. The volume of the reaction vessel is increased. Okay, so the rule here again is if you increase the volume of a gaseous equilibrium, or a system in gaseous equilibrium, if you have mostly gases basically, that is, then the equilibrium will shift, okay, towards the direction of more number of moles of gas produced. Okay, so that's the rule. And again, keep in mind that this is also equal to a decrease in pressure of the reactant gases. Okay, so the volume of the reaction vessel is increased. So how many total gas moles do we have on the reactant side?
7.
7, okay, we have 7 here. And then how many total product moles do we have on the product side? 8, okay. So 7 is greater than 8, okay. And again, the rule is this will shift towards, since this is an increase in volume, so it will shift towards the right, okay. So therefore, what will happen to the concentration of ammonia? If your reaction now favors products, it will decrease. Sorry, this is very, it will decrease. Okay, it will decrease. All right, what happens if you, hello, I can hear you. Good morning. What happens if you heat the system? Okay, oops, sorry about that. So what happens next as you heat the system? Let's just clear things first before everything here is crowded. Okay, so if you heat the system, what is this reaction? Is this exothermic or endothermic? Anyone?
Endo?
Huh?
Endo?
Remember that for a positive delta H,
negative.
that is a positive, yeah, for a positive delta H, that is endothermic, okay? But this is negative, so this should actually be exothermic. Okay, now again, what happens if you have an exothermic reaction? Do you release or absorb heat?
You release.
Absorb heat.
Release heat. Okay, release. So if you release heat, that means that heat can be considered as a product. Okay, so if the reaction vessel is heated, oh gosh. So first of all, the value of K will change. Okay, you don't have the same equilibrium constant anymore. Okay, but and as a consequence of that, what will happen is so you added more heat, which is a product. How do you get rid of that extra product?
Shift to the left.
The reaction should shift to the left, therefore. And what, sorry?
Using more reactants?
Yes, we see more reactants, basically. Yeah, so we produce more ammonia. Okay, and then lastly, what if you add a suitable catalyst to the reaction vessel?
No.
Nothing.
Okay, this is always no effect. But basically, I mean, if you want to be a little bit more particular, the rate at which the reaction will go to equilibrium is faster, but again, the equilibrium concentrations or the equilibrium ratios will still stay the same.
Okay, that makes sense.
What was that for letter E?
Letter E should be, since you have an increase in volume, so you're going from 7 to 8, okay, products to reactants. So this one should shift the reaction to the right, okay, and that would lead to a decrease in concentration of ammonia. Letter
And
E.
how are the coefficients related to the volume again?
So first of all, you should only consider gaseous moles. Okay, so basically, the rule for volume is if you increase volume, let's actually write that down over here. Okay, so the rule for volume is an increase in volume will shift the action towards side with more gaseous moles. Okay. And again, I'm emphasizing here gaseous because in some heterogeneous systems, that might you might have some solid, liquid, or aqueous components, in which case you don't count them. Okay, So for example here, let's say, so here in this equation, we have 7 total gas moles on the reactant side, all right? And then we have 8 total gas moles.
Make videos and send them to us, and then we're gonna have to do worksheets and submit them to online.
What was that? Then we have 8 total gas moles on the product side. Okay, so here, since you have an increase in volume, then the reaction should shift to the right, where you produce more gases. Okay? Now, what if, for example, in this reaction, instead of this being water as a gas, this was water as a liquid? Okay? If that was water as a liquid, then how many total gas moles do you have only on the product side?
2.
You only have 2. So again, if water was a liquid and you still increase the volume of the reaction vessel, then it would have been a different story. What would happen then will be the reaction will shift to the left. Okay. Yeah, the reaction then would have shifted to the left because you now have more gaseous moles on the left. And in that scenario, again, only if water is a liquid, then will you have an increase in concentration of ammonia. Any questions?
Will this also count when, okay, so you said that only gaseous moles, but does that count when it's like aqueous solutions as well?
Aqueous does not count. This one for temperature actually only takes into, no, not temperature, but sorry, this one for volume and pressure only is for gases. But yeah, no, not aqueous solutions.
Okay.
Okay, that will actually close the chapter. Are there any questions? Okay, so for the sake of this exam, and just so that I want to complete this, basically, I'm allowing you to actually send this. I mean, you don't have to go to school. You can basically work on this on your own and then send me an email. Now, again, I want this as quick as possible. So send this to me by tomorrow at 3:00 p.m. Okay? Again, this one is tomorrow. Oh, this one is tomorrow. Tomorrow, the 17th at 3:00 p.m. Also, by the way, keep in mind that I will still be here during this, I guess, whatever this is. Okay, so with that, I'm closing the chapter for chapter 12. Let's now go to chapter 16, the remainder of it. Okay. Actually, readjusting the laptop. Okay, so chapter 16 is basically about Gibbs free energy again. And again, the main meat of chapter 16 is that the free energy actually represents the available energy for the reaction either to go forward or backward. If delta G is negative, then that just means that the value of K is huge. Okay, you have a great value of K, and I think I put it here. There you go. So again, if delta G is negative, the value of K is greater than 1. Okay, which means products are favored over reactants, which means the forward reaction is spontaneous. Okay, now if K was positive, if delta G was positive, then what we said before was the reaction is not spontaneous. Now that is true for the forward reaction. For the reverse reaction, that's actually spontaneous, meaning the reverse reaction is heavily favored, meaning that the reactants predominate over products. And in terms of equilibrium, you have a K value less than 1. All right. And at rare cases, you'll have a delta G equal to 0. So that just means that your K value is approximately equal to 1, but that's very rare. Okay, let's go answer this problem, 16.66. Okay, we're asked here to calculate delta G for the reaction, and you're given that reaction and the following conditions. Okay, so to answer this question, first we have to write the expression for delta G. So delta G, or not expression for delta G, we have to remember that we are going to use this equation. Delta G is equal to delta G naught plus RT ln of Q. ln of Q. Okay, there you go. Still getting used to my new stylus, sorry. Okay, so and then after that, we can first solve for delta G naught. Okay, delta G naught, which means basically standard conditions. We can use these values for delta G of formation at standard conditions. So to do that, we just do products minus reactants. So that will be on the product side. Oops, oh gosh. On the product side, we have 3 moles of sulfur. Okay, 3 moles of sulfur. Now for sulfur, you don't actually have thermodynamic data for sulfur, but that is just because rhombic sulfur is the standard state. Okay, so that's the standard state of sulfur, which means basically that this delta G of formation, okay, this delta G of formation is equal to 0. Okay, at that point, are there any questions? Why the delta G of formation for sulfur in its rhombic phase is 0? No? Okay, so there are no questions, so let's proceed with this one. So again, delta G is equal to 0. Have to bear with me with that, I guess, for the rest of this thing. Okay, times 0. And then plus, what are you going to add with this term next? So this is again products minus reactants. What are you going to add next?
34.
Huh? Sorry?
2 times negative 34.
Well, keep in mind, this is products minus reactants first. So we're only looking for now at the product side.
It would be 2 times negative 229.
Times negative 229. So this is basically what you guys have did like at the first part of this chapter and what we did in chapter 7 last semester. Okay, 2 times negative 229 joules per mole or kilojoules per mole. Okay. So that will be the product side. How about the reactant side? Anyone?
Negative 300 plus 2 times negative 34.
Okay, so the reactants will be H2S plus SO2, so that's going to be 2 moles of negative 34 kilojoules per mole. All right, and then that is plus 1 mole for SO2, negative 300 kilojoules per mole. Right. And can someone give the number for me here, please? This is just still like we are working problems in the class together.
Negative 90 kilojoules.
Yeah, negative 90 kilojoules. Did anyone else get a different answer? Okay. So after that, now that we have a value for delta G, we're going to calculate for, or a delta G naught, we're going to have to calculate for delta G. Okay, let me try to do this again. I just want to create a new slide. We exit this thing. Okay. Not sure how to exit this thing. Let me just exit this, okay? Sorry. Keep. Then slide, there we go. Okay, so now that we have delta G naught equal to negative 90 kilojoules, okay, we can plug in that value to solve for delta G, okay? So delta G again is equal to delta G naught plus RT ln of Q, okay? Let's write first an expression for Q, okay? The expression for Q is partial pressure of water, okay? So this is just, again, Q, so similar to K squared, divided by partial pressure of H2S, okay, squared, times the partial pressure of sulfur dioxide squared. Okay, so once you have all of these, we just put them all in this equation, which will just become negative 90 kilojoules. Okay, at this point, I'm going to stop. Remember that the value here for R that you're going to use is 8.314 joules per mole Kelvin. Okay? Now, what you can do is either convert this value, 8.314 joules per mole Kelvin, or convert this kilojoule value instead. I think I'd like to convert this one. Okay, so to do that, what we're going to do instead of writing negative 90 will be to write negative 90,000, okay, joules plus 8.314, okay, joules per mole Kelvin. When we're done with all of these problems for chapter 16, basically for equilibrium, let's go over some problems again wherein we'll have to use, wherein we'll discuss where we need to use what value for R, okay? And then times temperature, this one has to be in Kelvin, so 298 Kelvin, okay? Times ln of Q, and Q again is this expression. But if we plug in the partial pressure values, so the partial pressure of water is 0.030 atmospheres squared divided by 1.0 times 10 to the negative 4 atmosphere squared times 0.010 atmospheres. All right. And then that's another whatever. Does everyone follow, or is anyone lost at what I've done here so far? Any questions?
That coefficient for H2S, that's negative 11?
No, sorry, negative 4.
Oh, okay,
Negative 4.
sorry.
Negative 4, that's fine. Yeah.
I think I may have gotten a different value for delta G.
Really?
Standard state.
Okay, what did you get?
I got 826.
Are you subtracting or are you adding? Because I added earlier and I got 826, but when I subtracted it, I got negative 90.
I thought I subtracted it.
Right, yeah, so make sure that this is, okay, if we can, let's just go back to this one really quick. So for this one, you will end up with negative 458 kilojoules for the product side, and then that's going to be, oops, shucks. It's going to be minus negative 368 kilojoules.
I had put positive 229, not negative 229.
Right, yeah. Oh, there we go, yeah. Okay, sounds good. All right. So after doing this, what will be the answer to this one? Let's further simplify. No, I cannot simplify. Sorry, I don't have the notes. So anyone, what would be the answer to this one? So that's going to be negative 90,000, okay, joules, plus 2,478, correct me if I'm wrong, okay, and then times 16.01, I think, 16.01, 16.
negative 3.57 times 10 to the negative 9.
That's not what I got.
I got 1, 2, negative 5.0 times 10 to the 4th.
Yes, yeah, that's the correct answer. So this one will actually end up to be a gift from Zoom. We removed the time meter. Fine. Okay. So this will actually be, and this will actually end up to be positive. Fine. Do you want to learn some chemistry too? You want to be the next Nobel Prize winner? Joules. Okay, so yeah, so that will end up to be 50,000 joules, which will just end up to be 50.3 kilojoules. Are there any questions? No? Okay, if there are, what, sorry?
I said no, sir.
Okay, let's move now to this slide. So, okay, again, we were looking at this equation, delta G naught plus RT ln of Q. So keep in mind again that delta G naught is only if you have standard conditions, okay? Standard conditions which were specified in this slide. There we go. Yeah, so usually 1 atmosphere, solute at 1 molar, and then temperature usually at 25. But as we have seen for this previous problem that we just actually worked at, none of the gases were at 1 atmosphere. That's why we had to calculate for delta G. Okay, so now in cases where you actually have standard conditions, in cases where you are actually at equilibrium, so this equation further simplifies basically into this, wherein delta G is equal to 0, and Q is equal to K. So again, this is only if you have a system in equilibrium, only if in equilibrium, okay? So let's work on the next problem, 12.67. Okay, let's say for example, you have the following conditions for each of the following mixtures. Let's predict the direction at which the reaction will shift to reach equilibrium. Okay, let me just create few more slides before we actually proceed. Okay. Okay, one second. Okay, well, I didn't like its position, but whatever. Okay, so for this case, we have to first know actually if, well, your system is in equilibrium. It was not actually mentioned that the system is in equilibrium. So let's work on letter A, conditions letter A. Okay, so for every case here, you're going to use delta G is equal to delta G naught plus RT ln of Q. Okay. Now, the expression for Q here should be pressure of N2O4, all right, divided by pressure squared of nitrogen dioxide. Okay. Now, delta G here, okay, so delta G naught for all cases, again, this is for all cases, okay, will just be products minus reactants. So, products, what do we have for products? Dinitrogen pentoxide, or tetroxide. Okay, let's move this out of the way. Okay, dinitrogen tetroxide, so this one will be, 1 mole times 98 kilojoules per mole. Okay, and then that will be subtracted with 2 moles. Okay, 2 moles, and then that will be 2 moles times 52 kilojoules per mole. Okay, sorry, it's a little bit messy. Okay, and this one should just give you, I'm gonna give you just the answer for this one, for delta G, negative 6 kilojoules. Okay, so that's delta G naught. If you don't get the same number, let me know. Okay, so if we want to solve here for, hello. So solving here for delta G, so solving here for delta G, what we get is negative 6 kilojoules, okay? And then that is plus RT ln of Q, so that will be 0.314. Well, let's actually express this as negative 6,000 first. Negative 6,000 joules, okay, plus 8.314, okay, joules per mole Kelvin, okay, times the temperature here is 298 Kelvin, okay, and then times ln of pressure of nitrogen, dinitrogen tetroxide is 1 atmosphere, okay, and then pressure of nitrogen dioxide is 1 atmosphere. That value is squared, okay. Now, at this point, this entire term is actually 1, and if you know the laws of logarithms, remember that ln of 1 is equal to 0. Okay, so this term actually is 0, meaning this entire term is 0. So here, delta G is actually just equal to negative 6 kilojoules. Okay, and what this actually tells you is this reaction is in standard conditions. Okay, now if delta G is negative, that means that the reaction is spontaneous in the forward direction. So here, the reaction will tend to shift. Will tend to shift to the right to reach equilibrium. Okay? Are there any questions with that one?
Does it matter which pressure you use for Q?
What do you mean which pressure?
Like how there's A, B, C.
No, we're only working at A, sorry. We're working at A right now only. Yeah, we're taking it, this is 3 problems actually.
Oh, okay.
Yeah, okay. Any questions again? So again, this should be delta G is equal to negative 6 kilojoules. This just means that delta G is equal to delta G is equal to delta G naught. Any questions? Okay.
In the previous slide, it says the ln of K, and then in the next one we used ln of Q. Is that because you can interchange them with that formula, with the pressures?
No, this.
Isn't it because you said that, like, in the last slide, it was like because Q is equal to K? Like for the specific conditions?
Yeah, Q is equal to K only if you are in equilibrium. So I guess my bad here is I placed this problem right after this slide. We are trying to determine here, first of all, if the system's in equilibrium. That's what we're trying to do. So here, what we're trying to do is, upon calculating the value of delta G, if it is negative, then it's not yet at equilibrium. It has to shift to the right. If it is positive, it's not yet at equilibrium. It has to shift to the left. Okay. And then if we get a delta G equal to 0, then it is at equilibrium. Okay. So that's why we actually used this equation instead. So this equation again is only if we are sure that the system is in equilibrium. Okay. At this point, we're trying to figure out whether it's in equilibrium or not. Does that clarify everything? I'm sorry. Hello?
Yeah.
Okay, good. So, sorry. Okay, and then yes, these are, by the way, 3 separate problems: letter A, letter B, and letter C. Okay, so letter A definitely then is not at equilibrium. Okay, so basically that's just the point of letter A. Okay, now let's go to letter B. Okay, for letter B, you have, well, just look at your slides because you have the following conditions, 0.21 and 0.50 atmospheres of pressure for nitrogen dioxide, or sorry, this should be nitrogen dioxide, now that I see it, nitrogen dioxide and dinitrogen tetroxide. Okay, so for letter B, we're again going to use the equation delta G is equal to G is equal to delta G naught plus T ln of Q. Okay. For this case, again, delta G, we have solved that previously, is negative 6,000 kilojoules, all right, plus 8.314, all right, joules per Kelvin times 298 Kelvin, all right, and then plus or multiplied with ln of 0.50 atmospheres, all right, divided by 0.21 atmospheres. That is squared. All right. So now that you have this, if you further simplify this, you'll actually get negative 6,000 kilojoules plus what will be this part of the equation? Anyone?
Six thousand 15.9.
Yes, yeah. So 6,016, let's just say. Okay, kilojoules. 6,016 kilojoules. Okay, and then this will just end up to be, no, not kilojoules, sorry. This is actually joules, everything. So this is not kilojoules, my bad. Okay, so that is just joules. Okay, because we converted them already. Okay, so this one is 16,000 joules. Okay, and this will give you negative 16 joules. Okay, now, and that should be...
Wouldn't it give you positive?
Yes, sorry, positive, yes. Now, I will argue out that this value is very small, okay? I mean, that's not even enough calories for a snack, not even for a single grain of rice, if I will be that very descriptive. So I will say that that value is very small, very negligible, that we can assume, okay, that the delta G for this reaction is actually 0, okay? And if, again, you have delta G equal to 0, then that means Q, then that means the value of Q is equal to K. Go away. Sorry. Then that means that Q is equal to K, okay? And that means that the system is in equilibrium, okay? System is in equilibrium. Okay, does that make sense? Like the approximation why I did say that 16 joules is a very negligible number anyway. So if that doesn't make sense, just let me know. But again, keep in mind that this is 16 joules, okay? In the food that you intake, let's say, for example, if a pack of crackers that you see when you buy it from a grocery store says around 200 calories, capital C, then that's actually around 8,000 kilojoules of energy, okay? So this is really, really small. Not even, again, a grain of rice. All right, let's now go with letter C, final conditions, okay? So for letter C, that one will just be, again, using the same formula, delta G is equal to negative 6,000 plus RT, so that's going to be 8.314 joules per mole Kelvin. All right, times 298 Kelvin. All right, and then the conditions for letter C will be okay, the conditions for letter C will be ln of let's look at the numbers. Okay, the numbers are 1.6 and 0.29. So that should be ln of 1.6 atmospheres, okay, divided by, oh wait, divided by 0.29 atmospheres squared. Okay. And what will this number be? I'll provide you with this one. So this should be negative 6,000 joules. And then this entire thing, oh Christ. Okay, this entire thing is just plus 7,298 joules. What is this value?
1,290.
Yeah. So this one should be positive 1,298 joules, which is just 1.3 kilojoules. Okay, so here the delta G is positive. So where do you think the reaction should go to reach equilibrium?
To the left?
Yeah, basically to the left. Yeah, so basically towards reactant formation. Yeah. So that's just what this means. Okay, so this one should favor, or not favors, but to reach equilibrium, equilibrium must shift to the left. All right. Any questions?
I have a question about part B.
Yeah, sure.
For the, like, how you got 16 joules and you said that was like a negligible amount. Like, around what range of values would you consider like a negligible energy?
Yeah, that's a good question.
Sorry.
No problem. Okay, that's a good question. I'll say anything with an absolute value of 100 joules and below. Yeah, so there we go, 100 joules and below. And again, no problem. That's a very good question. And again, the argument here is that 16 joules is not enough to burn even a grain of rice. Okay. Any other questions? Okay, I'm looking at my clock right now and it says 9:20. So I think we have one more question, which is basically every question here in chapter 16. We're going to start with chapter 13 on Monday, but I'll spend the rest of the class hour basically asking if the class has any questions or whatever. Okay, but let's work on this last problem. Okay, hydrogen sulfide can be removed from natural gas, blah, blah, blah. Would this reaction be favored at a high or at a low temperature? Okay, so one thing I guess that this problem doesn't say is that this reaction is at equilibrium, okay? So this is at equilibrium. Okay, so if this is at equilibrium, so that just means that delta G is equal to 0 and Q is equal to K. So the equation that we're going to use here is delta G naught equal to negative RT ln of K. Okay? So delta G can be solved using these delta G of formation values. Again, there's no sulfur because that's the standard state of sulfur, just monatomic sulfur. Okay? So here, delta G naught is equal to, what do we write here first for products? So we have 3 moles of sulfur times 0, okay? And then plus, what do we write next?
Two
2 times water.
Yeah, 2 times water, which is 229, negative 229. So 2 moles times negative 229 kilojoules. Sorry.
The
Sorry, I didn't hear that much, Sam.
Sorry, my internet connection is bad. But this looks like it's the same equation as the beginning of the session, so wouldn't that just be the 90 we were dealing with earlier?
What do you mean? Oh, like this one? Like this one? That's what you're saying?
No, like when we were calculating for the G naught.
Yeah, that's what we're doing. So actually here, I think I should have been more specific. You're actually trying to, so basically you can determine this. That's what we're trying to find out, okay? You actually know this as well. You know the temperature. It's given as 298 Kelvin. So the thing here, which you don't know, is actually the value of K, okay? So because, well, it actually tells you calculate the value of delta G and calculate the value of K. Okay, so, and then the next question should be, is it going to be favored at the high or at the low temperature? But we'll get to that. Okay, so we're calculating it step by step first, delta G and then K. Does that answer that question? I hope. Hello?
Yes, sir.
Sounds good. Just checking. All right, so that should be plus, or there you go. That should be per mole. And this should be minus 2 times, we're now working on the reactant side, 2 times negative 34 kilojoules per mole. All right, and then this one is plus SO2, so that's 1 mole times negative 300 kilojoules per mole. All right. Okay. And then, can anyone solve this for me, please? Yeah. What will be the value of delta G naught?
Negative 90.
Negative 90.
Yeah. So that's going to be negative 90 kilojoules. Okay, but we're not yet done. That only takes care of delta G naught. We still have to determine what the value of K is. Okay. So given that delta G naught is equal to negative 90, so again, we're going to use this equation, delta G naught is equal to minus RT ln of K, okay? And for that, we just plug in whatever values we have, so that's going to be negative. Let us actually, at this point, express delta G in terms of joules, okay? Because again, R is in terms of joules. So it's going to be negative 90,000 joules, okay? And that's going to be equal to negative let's erase that. So that's going to be equal to negative 8.314 joules per mole Kelvin times 298 Kelvin, right, times ln of K. All right. So for this one, we just get ln of K equal to, ln of K is equal to negative 90,000 joules divided by 8.314. 8.314 joules per Kelvin, then times 298. Okay. 1 second, yeah. Okay. Okay, there you go. And then you should have a negative sign too. Okay. And what should be the answer to this one then?
36.3.
6.3. Wait 1 second. I think I screwed something up. Let me see. Sorry. Okay, delta G R T.
That's ln K, so then you'd have to E it.
Yeah, no. But I think there should be no negative sign. I'm not sure where I went wrong.
Oh no, there is. I got positive 36.3 as well.
Okay, sounds good. Sorry, okay, that's the number I got then. Sorry about that. Okay, so this should be, I got confused. So this one should be ln of K is equal to, or K should be equal to E of exp of that. Okay, so that should be K is equal to E raised to 36.32, right? Okay, And what is and the value for K should be, what's the value for K?
5.9.
5.97.
5.9 times 10 to the 15th.
To the 15th. Okay. So that's a very huge value for K. So that actually means that this is, this actually means that this reaction is products favored, right? Products favored. Okay. Now, if this is products favored, what can you surmise about the sign for delta G? If this products favored, what do you think will be the sign for delta G?
Negative.
Negative. Well, because it's products favored, so the forward direction actually proceeds as it is written. So delta G here should be negative. Okay. Now, let's look at the equation again, because we're actually asked, okay, is this going to work at the high temperature or at the low temperature? Okay, let's look at the reaction again. So here, okay, so here, look at this reaction. Comment on the delta S of this reaction. Is it going to be a positive sign or a negative sign? So we're going back to the first chapter that we discussed in class. So,
Negative.
Yes. Oh gosh, that was horrible. Sorry. Yes, so this will be negative. Okay, that freaks me out. Okay, so this will be negative because you're going from 3 gas moles to 5 gas moles. So this will be negative. Okay.
Oh wait, it's only 2 because sulfur's solid.
Oh, sulfur solid. Sorry, it's 3 to 2. Sorry. Yeah. Right.
So it would be positive, right?
No, this will still be negative because you're actually less ordered. Sorry.
Oh, okay.
Yeah, sorry, it's the logic. But yeah, this would be 3 to 2. Thanks for catching that, Sam. Okay, we have only 1 more minute. So basically, let's just continue with this one. So if delta G is equal to delta H minus T delta S, remember, if delta G is negative, if delta S is negative as well, and delta G is negative, and delta S is negative, then for this reaction to be spontaneous, okay, delta H must be, come back. Sorry, this thing won't cooperate with me. Then this thing should be negative, okay? Now, if this should be negative, then temperature, therefore, should be very low. Okay, this one should be low. Okay, let me explain this again when we meet again on Wednesday. It's just that we're short with time, but thank you for being patient. I'll see you again on Wednesday. And again, if you have questions, I'm just here in my office.
Thank you.
No problem. Bye-bye. End meeting. Okay, there you go.